So today we're starting the Laplace transform, and what we'll do the rest of the remaining lectures is do these generalizations of the Fourier transform. That's the Laplace transform for continuous time and the Z transform for discrete time. So let me note that here. This is continuous time only. Let's use our usual abbreviation, CT only. Okay, so we have a continuous time signal. Now, why do we need something new other than the Fourier transform? Well, a couple of reasons that we'll want this generalization. There will be signals that don't have a Fourier transform, and the Laplace transform is sometimes applicable then. What would make a signal not have a Fourier transform? The integral doesn't converge. So if it has infinite energy, that's going to be a signal that the Fourier transform doesn't work for. Okay. And I'll say that infinite energy there. And also, if we have an unstable system, then the Laplace transform is going to allow us to analyze systems even whether they're stable or not. And that's actually very important for control. So control is one of the main applications of the material we'll learn here with the Laplace transform. And I put in parentheses differential equations. We saw in the previous lecture that we could use the Fourier transform to solve a differential equation. Right? What was the example? Did anyone watch that extra recorded part of the lecture? What was that? We used the derivative property, and it was a circuit example. So we showed that this circuit that you would solve with the differential equation, we could actually immediately solve it with the Fourier transform. Although that technique with the Fourier transform only works if you know the system's stable. And in general, you should use the Laplace transform. We'll see it's the same method, but it's going to work more generally. Okay, so what is the Laplace transform? Well, here's the formula. X, we'll use capital X like we do for Fourier, of the variable S is the following integral. Okay, so if we have a signal x of t, this is our signal, then its Laplace transform is this function. It's this integral with the variable in the integral. Now, S here is complex. So unlike the Fourier transform where we had a frequency f that was real, here we have a complex valued S. Okay? So in other words, the domain of x of S is the complex plane. What? Instead of like just you're saying a circle. Yeah. Well, for the Fourier transform, the domain was just like frequency f, right? So for any real valued frequency, and here it's a complex number s. All right. So it's going to be difficult to plot this, right? We already had a hard time plotting the Fourier transform. It was because you have complex values at the output, right? Well, the value of x of the Laplace transform is complex, but the domain is also complex. You would need a four-dimensional plot, right, if you wanted to capture the whole thing. Okay. So some important notes about this. This may only converge for some values of S. And that actually is very important, and we'll talk about that. So it's not like you say, well, you either do have a Fourier transform or you don't. Here you have a Laplace transform, but only for some subset of values of S. So in other words, the Laplace transform actually has two parts. You have this, the first part is the region of convergence. And we abbreviate that ROC. And then the second part is actually the value of this of the function x of s. So to fully specify a Laplace transform, you don't just say say you have a formula for capital X of S. That's not enough to fully specify it. The region of convergence is another part that's needed to specify what the Laplace transform is. Okay, let's do some examples that'll help here. So first of all, let's look at this. Let's let x of t equal e to the t u of t. All right, what is this? You probably have already done the Fourier transform of a signal like this. For example, u of t e to the negative t. All right, I believe somewhere along the line, maybe in a problem set, you've done that Fourier transform. Okay, but here there's a difference. I have e to the positive t. So let's plot what this is. Here is what e to the t u of t looks like. Starts at 0 and it grows exponentially. Okay. Now, does this have a Fourier transform? No, it doesn't. Right? This has infinite energy. So there's no Fourier transform here. Energy is infinite. But the Laplace transform as a generalization allows us to still do something to this signal. Okay? So let's try the integral here and see what the Laplace transform is. So we could plug in. So we would say, x of s equals integral of e to the t u of t e to the negative st dt. Okay. Now, we can integrate this. We can combine the exponents together. Well, first of all, we should bring the u of t into the limits of the integral. So we get equals the integral from 0 to infinity of e to the 1 minus s t dt. Okay. Now s is complex, but doing this integral is the same as we would if it was real valued. It's going to be 1 over 1 minus s e to the 1 minus s t evaluated t equals 0 to infinity. All right. Now, there's one thing we might note here. Let's say the infinity is going to be 0 if a certain condition. We'll talk about the condition in a minute. So this is going, in the case we're interested in, the infinity, when you plug in infinity, you're going to get 0. So this is going to be negative 1 over 1 minus s equals 1 over s minus 1. Okay, so that's the value. Now let's talk about when did this converge. Okay, I skipped over steps. This integral doesn't always work. What would be the condition for which, really look at this second line here. What would be the condition on s for this integral to converge? Okay, so you're right. It's going to be something about s being greater than 1 because you want the exponent to be negative, right? But it's actually not absolute value. It's the real part. Okay, so the real part of s should be greater than 1. And to see that, so here, like I said, the region of convergence is an integral part of this Laplace transform. Yes? But the imaginary part of the exponent just cycles, exactly. It doesn't grow, right? So it's just the real part that causes growth. All right, so the real part of s should be greater than 1. Okay, so this is the region of convergence there. If the real part of s is greater than 1, then this Laplace transform converges. Again, let's just look at that. Why was it the real part? Because this is, look at this function. Here, let's use another color. Look at this thing, e to the 1 minus s that we were trying to integrate. This is e to the, or actually it was with a t, right? This is e to the 1 minus the real part of s t times e to the I, negative I imaginary part of s t. Now all the variables are real variables here, like the real part and the imaginary part. Those are just real numbers. And this part is exponential growth or decay, depending on the exponent. Okay, and this part is just complex exponential, like the way we think of this is like a sinusoidal, let's say periodic. Oh, that's okay because this part here will be 0. So it'll be like 0 times a cosine or a sine. Yeah. So in other words, once we split it out, it's the real part that determines whether it's going to converge. In fact, we'll see that in a moment. We'll see that the real part of S is all that's going to matter for whether it converges or not. Okay. So let's go back here and say, okay, we now have, here we have the whole thing specified. We have the region of convergence, and we have the formula for the Laplace transform. So there's a fully specified Laplace transform for that signal. So even though this had no Fourier transform, it had infinite energy, we actually do have a Laplace transform. Yes?
Sorry, just the limit there is still sort of bothering me and bothered me before when we were doing this. It's like,
yeah.
You can say like this limits to 0 if picking some distance from 0, you can find some number large enough that past that number you're always that close. But since this always has like magnitude 1,
yes.
There's never any number where you can say this will be always closer than like 0.5.
You're right. So this doesn't converge. This one converges to 0. But the product of two, this is just bounded, right? So the product of one converging to 0, if the other one's bounded, then the product converges. Yeah, but good point. All right, so suppose that, now I want to do a second example, and hopefully you'll see why this is a nice complementary example here. Let's do this example. X of t equals negative e to the negative t u of negative t. A lot of negatives in there. All right, let's plot this thing. So this has a u of negative t, so that means it's 0 for positive values of t, right? It's the opposite. It's going the other way. And this is now an exponentially decaying signal, but because we're going backwards, it's still the, let's see. Oh, do I have negative? Oh no, I want positive. Sorry, I don't want the this negative in the exponent. So I really want the same growing exponential, but I'm going to look at the back side of it. Okay. So this is the example. So now it's decaying in the backwards direction, right? Okay. So is there a Fourier transform for this signal? It has finite energy, so this should be fine. We could do a Fourier transform. But let's do the Laplace transform. So again, we're going to get x of s. All right. Negative, we can put the negative out front. E to the t, u of negative t, e to the negative st, dt. And that's going to be integral from negative infinity to 0 of e to the, and now it's going to be 1 minus s t. Starting to look kind of similar, all right, except the integral is a different set. Okay, so this will equal, well, we work it out. We'll get a negative 1 over 1 minus s times e to the 1 minus s t, evaluated from t equals negative infinity to 0. And under the case we care about, the negative infinity part is just going to be 0. So it's going to be just 1 over s minus 1. Wow. Confusing, huh? Look at that. It's the exact same Laplace transform. How could it be the same Laplace transform? After all, I'm saying this is a generalization of the Fourier transform. It's more powerful than the Fourier transform. We know we can reverse the Fourier transform. We can't have two different signals giving us the same Fourier transform, right? But here we have two different signals, and they have the same Laplace transform. So what's going on? Different region of convergence. Remember, this is only a part of the Laplace transform. Okay, so the region of convergence here is what? What will the value of S? Remember, it's only going to depend on the real part. The imaginary part doesn't matter here. So for what real values of S will this converge? It's not any. It's not any because it's going to negative infinity here. So if the real part... Yeah, so now we need this exponent, right? We need the real part. I'll write it this way. We need the real part of 1 minus S. Okay? We need that to be positive because it's going to negative infinity. T has a negative infinity there. So this has to be greater than 0. Therefore, the real part of S should be less than 1. There is the region of convergence. Now we see something interesting. It's exactly complementary to the other set. So the region of convergence here was real part of S greater than 1, and here it's less than 1. Okay. So I want you to realize that you can have the same formula for a Laplace transform over different regions of convergence. The regions of convergence then will define what signal you're actually talking about. There's something else to notice here. We're going to connect this more directly to the Fourier transform, and then we'll come back to this second example here in a minute. So, okay, let's consider if we let S equal, if we split out and explicitly give variables for its real and imaginary parts. Let's say it's sigma plus I 2 pi f. Okay, so now we have sigma and f both real, and they're defining S for us, right? That's kind of the real part and imaginary part. Real. Okay. So we can write S that way. Then what do we have? We have that x of S evaluated at this, under this description. Okay. This equals, let's plug it in. And instead of S, we'll just substitute what we have, sigma and the imaginary part, I 2 pi f t dt. And we can recognize this as the Fourier transform of x of t times e to the negative sigma t. So what we have here is that for any the Laplace transform is a Fourier transform of our signal that's multiplied by a real exponential. Okay, an exponential that's growing or shrinking depending on what sigma we choose. All right. So, for example, if we evaluate it, if we let sigma be 0, okay, so we just let S equal I 2 pi f. Let S be purely imaginary. Well, then you see that, of course, this is just the Fourier transform of x of t. Okay, so the Fourier transform is the Laplace transform evaluated at S being purely imaginary. All right. Now we can actually denote it. Now notice I'm using capital X for the Laplace transform, and I also used capital X for the Fourier transform. That could be confusing if the context wasn't clear, right? So sometimes to clarify the context, I'll put a little X sub L for Laplace, just for the lectures. So usually I don't need it because you know what I'm talking about. So I could write this. Let me use red here. I could write it this way. I could say that this is X L of, and I could just plug in sigma plus I 2 pi f. And now that I'm explicitly saying this is a Laplace transform, then that notation wouldn't be too confusing. Okay, and here I could say X L of I 2 pi f. Okay, so then you can summarize these by saying, this is kind of fun, then XL of I 2 pi f actually equals X Fourier, maybe I'll put a little f down there, of f. Okay, so we just wrapped all that into notation. Okay, good. Now let's interpret the Laplace transform a little bit further. then with this understanding. So all right. Then suppose we have some signal. So remember, we're using what we just talked about above, that the Laplace transform at some sigma plus I 2 pi f is the Fourier transform of a signal x of t e to the negative sigma t. So think about this. You have some signal. Here I'm going to just suppose it's you have some arbitrary signal that you're trying to analyze. But suppose that it's sort of growing. Okay, it's growing such that you couldn't do a Fourier transform. Okay, it has infinite energy. Well, you might want to use Fourier analysis, but in order to use it, you can first multiply it by some real exponential. And the job of this real exponential is to taper it off. So think of here's some exponential function. This is e to the negative sigma t. You pick a sigma, multiply it, and now the result of this multiplication might be something with finite energy. Okay, so maybe it looks like, I'm practicing my drawing skills here. Suppose you taper it off strongly enough that it now decays. Okay, now you could take a Fourier transform. And that's what the Laplace transform allows you to do. It allows you to pick a sigma that tapers it off, and then do a Fourier transform. Okay, so for some sigma this will work, and for some it won't. So if sigma is large enough, then the Fourier transform might exist. You could come up with a signal for which you can't ever make this converge. In other words, the Laplace transform region of convergence would be nothing. That's possible. There's a couple ways to do that. It's not that interesting to us. I mean, one way is just have it have a vertical asymptote somewhere that doesn't integrate well. Okay. Another way, even if it has no vertical asymptote, is that it can grow super exponentially, so that no exponential function could make it converge. Okay. But you might be able to get it to converge this way. Notice this. If sigma is too large or too small, then you can cause it to diverge. What I want you to notice about this is you might think, well, I could just, bigger sigma is always going to be better to make this converge. Why would that not be true? Why picking sigma too big could you actually cause this convergence to not hold anymore? Yes, so my example wouldn't be a great example of this because I drew this signal starting at some point. But a signal could go in both directions, positive t and negative t. And you could get the negative t part to not converge. Because off in that direction for positive sigma, you're actually growing the signal, right? So there's going to be some set of sigma for which it might converge. Make it too big, too small, might not. All right. So that's a way to interpret this. Okay, so let's think about this complex plane where the values of S live. All right, so here's the complex plane, and what we're going to plot is the domain of S. So this is the real part of S in this direction, the imaginary part of S in this direction. Okay, now, for each value of S, there's first of all, there's a region of convergence. And within the region of convergence, for any value of S in that region of convergence, you have a complex valued Laplace transform. Okay, so I'm not going to draw a four-dimensional plot here, but I am going to point out that the Fourier transform lives on this line. So this is, if you just take the slice of the Laplace transform on that line, you get the Fourier transform. Okay? If you take a slice of another slice, another vertical slice, let's say right here, okay, that's another value of sigma, right? We'll call it sigma naught. So that's another constant value of sigma. That slice is the Fourier transform of x of t e to the negative sigma t. So it's another sigma. It's that tapered off x of t. So what we really have in the Laplace transform is a bunch of Fourier transforms, the same signal, just with a different exponential attached to it. So what that means is, for example, this Laplace transform is very redundant. Any one of these vertical slices contains all the information about x of t. Okay, right? Because the Fourier transform contains all the information about x of t because you can invert it. Okay, so it's very redundant in that way. Now, these statements I said are only true if these vertical lines are in the region of convergence, right? If they're not in the region of convergence, they're meaningless. But if they're in the region of convergence, then what I said about this being the Fourier transform and that being a Fourier transform of a different signal is going to be true. So, and of course, I'll just highlight the comments we've seen so far. The real part of S is sigma, which is the exponential decay that we're connecting to our signal. And the imaginary part of S is 2 pi f. So it's the frequency. So really, you can think about S. If you want to, S is complex value. Think about its real part is this decay, and its imaginary part is a frequency. Okay. Now, let's do another example, which I can actually do a 4-dimensional plot for. Okay. So that'll be fun. Here's another example. Let's let x of t equal rect of t. Now, we know if we were doing the Fourier transform, then we would get sinc of f. Okay, that's the Fourier transform of rect of t. But let's now do the Laplace transform. So x of s equals the integral rect of t e to the negative st dt. And we'll take rect into the limits here. So it's negative half to half e to the negative st dt. And that's going to just be e to the negative s over 2 minus e to the s over 2 all over 2. Okay, so there is, now, what about the region of convergence? I always kind of jump ahead as if these integrals converge, but we didn't talk about for which s will this converge? Where'd the half come from? Oh, whoops, that's not a 2. You're right. Reading my notes wrong. This is over S. Thank you. Yep, because when you integrate that, 1 over S comes out. Thanks. All right, so this function, so where for which S will this converge? This integral. What? Yeah, even 0, actually. But for 0, we would need another answer. But yeah. So let's say for all S, but you're right. Just like we needed when we did the Fourier transform of rect, this formula doesn't hold for s equals 0. But we could plug in the integral for s equals 0. That would be the integral of 1, right? And that width is 1, so it would be 1. So we should really say it's this value for non-zero s, and it's 1 for s equals 0. Fortunately, the limit of this as s goes to 0 is 1, so we don't worry too much about specifying that. Okay. Great. So that means we would say the ROC equals the complex plane. Okay, if it converges for all s, right? So the region of convergence is everywhere. There's a reason why this converges everywhere. It's always going to be true for finite duration signals. So notice that rect has a definite beginning and end, right? There's points after which it's 0 in both directions of t. we call that finite duration. We'll talk a little more about that momentarily. And that is why you get it converging everywhere. Okay. If it's finite duration, it's either going to converge everywhere or it'll converge nowhere if you have these if you have a signal that has a vertical asymptote. Okay, so if you care about the edge cases mathematically, then it could converge nowhere or anywhere. What we care about is always going to converge everywhere. Okay, so I actually have a plot of this. So let's look at what this Laplace transform is. All right, in MATLAB, I just plotted this function. Now, okay, so here it is. Let me rotate it. Assuming it cooperates with me. Okay. So this is the four-dimensional plot. Now, why do I say four-dimensional? How did I plot this? Well, first of all, the domain here is the values of S, right? This is the imaginary direction, and this is the real direction. Okay. So this is the real part of S, which we're calling sigma. This is the imaginary part, which you can think of as the frequency. Okay. Now, we have the value of x of s is complex. And what I'm plotting in this plot is the magnitude of x of s, so the absolute value. But I'm using the color to plot the phase. Okay, so any complex number, we could do magnitude and phase. So here's the color chart for the phase. 0 phase, up to pi, and to negative pi. Of course, it wraps around, right? So these parts that look discontinuous, it looks like the phase kind of jumps discontinuously, but that's not really discontinuous. You're just going around. You're getting greater than pi, and that's making you the same as a negative value. Okay. So what I want to point out to you mostly is that, remember, the Fourier transform has something to do with this Laplace transform. How can we pick out of this the Fourier transform of this signal, which was rect? How can we get that out of this? Yes? So cut down the sigma equals 0 line, so this imaginary axis. Look at the imaginary axis, and that should be the Fourier transform. Remember, the Fourier transform of rect is sinc, right? It's a real valued sinc. Well, yeah, does that look like a sinc? Here, let me put it sideways. Does that look like sinc? It does. Sinc we usually draw going under. But this is the absolute value of sinc. Remember, I'm plotting the absolute value. And the fact that it should be negative here should be reflected in the phase. You see the phase changes as it goes across there. So there you go. There's your Fourier transform. I want that, if you get anything out of this plot, because we're not generally, for signal analysis, you don't usually use the Laplace transform. You use the Fourier transform. So you're not often going to actually be looking at plots like this. But what I want this to illustrate to you is that the Fourier transform lives on the imaginary axis. That's an important point to remember. Maybe this example will help that concepts be more solidified. Okay. So let me mention how would you take an inverse of this Laplace transform. I'm going to tell you the general way to take an inverse. It's actually not the way. It's good to know how it can be done, but it's not the way we'll ever use. Because we actually care about the Laplace transform for very simple cases, okay? And we'll see throughout this week those cases where we're going to use the Laplace transform for something powerful. For example, to solve a differential equation, all right? And so some of these properties of the Laplace transform are not actually needed for the many things we're going to do with the Laplace transform. But in general, what could you do? Well, one, if the imaginary axis is in the region of convergence, okay, then what? Then you take the inverse Fourier transform, right? Because then you have the Fourier transform just right there within the Laplace transform. So you just take the Laplace transform evaluated I2 pi f and take the inverse Fourier transform. Now, suppose that's not true, right? If that was true, we maybe wouldn't have even used Laplace transform. In general, you find a line that is in the region of convergence, and you do the inverse Fourier transform of that line. So you would always have x of t is the limit. I'll write out a formula that would be like the general formula. It's a plus there, minus in the bottom, plus in the top, x of s, e to the st, ds. The reason to write this out is just to show you, well, it looks sort of like an inverse Fourier transform. I mean, just like we expect, we get e to the st in there. We're doing some sort of integral. But the point is, and what's kind of wrapped up in this expression, is that so you do this for any sigma that puts this line in the region of convergence. So what this is really saying is just integrate. This here says limit of frequencies of f such that you keep the real part fixed and you just go over the imaginary line. It's saying just take any vertical line in the region of convergence and do an integral there of this thing. Okay, so basically just find any line in the region of convergence and do the integral. Now we could rewrite this in a way that maybe is simpler to internalize, and that's, if you plug in, you do a change of variables in ds to make it df, you're going to get that this is the integral from negative infinity to infinity. You're going to get this part comes out of the integral, and you're going to have x of the Laplace transform there of sigma plus I to pi f e to the I to pi f t df. And you can see that's exactly what we said in words to do. You're going to take a line within the region of convergence. You're going to do the inverse Fourier transform. And then you have to just get rid of that scaling. Okay, so it's quite straightforward. Like I said, we're not really going to use this form of the inverse. We're going to be doing inverses by inspection for what we care about. Okay, so great. Now, the region of convergence, we've said it only depends on the real part of S. So let's just discuss that for a little bit. The region of convergence is always a vertical, there are always vertical strips. So an example of a region of convergence in the complex plane would be something like this. We have our real part of S. We have our imaginary part of S. There's the complex plane. Some people might call this the S-plane. And your region of convergence is always of the form. There's some line, some vertical line, let's say 2 vertical lines, and everything between those lines converges. So this is the region of convergence. Okay, so that's the form of the region of convergence. It's always just going to depend on the real part of S. Now, it doesn't always have each of these boundaries. So the left or right boundary might not always be present. So in other words, it could just have like a left boundary, and every real value that's less than some number might not converge. But we saw that in our first example, right? When we did e to the t u of t, we had only one boundary on the region of convergence. We'll still call that a vertical strip, even if it doesn't have both boundaries. But it could have 2. Okay. So what about stability of a system? We've talked about stability, and I've mentioned that's one of the key reasons why we're going to do the Laplace transform. So let's talk about it right now. Let h of t be the impulse response of a system. Okay, so we've defined stability before, bounded input, bounded output. And now what we have is the system is stable if if the region of convergence of this Laplace transform, h of s, right, contains the imaginary axis. Contains the imaginary axis. Why is the imaginary axis relevant? It's the Fourier transform, right? So we're kind of saying if it has a Fourier transform, it's stable. Although I'm going to add a couple words that make it slightly different here, that it should have the imaginary axis in the interior. So what this means is should not the boundary of the region of convergence should not be right on the imaginary axis. So the interior just gets rid of the boundary itself. The interior of this region I drew up here is real values of s that are strictly within this interval but not equal to the edges. Okay? So if the imaginary axis, like this picture shows, if it's in the interior, then this system is stable. Okay? So, of course, it makes very good intuitive sense because that's the Fourier transform, right? Let me just give an example where the boundary matters. This is a weird example that should sort of illustrate why I had to say in the interior. Okay, so here's an example of an unusual case, that unusual case where the boundary is right on the imaginary axis. And this is actually going to be something you might have thought should be very relevant to us. Let's have the impulse response be the sinc function. Sinc is so important to us when we do sampling, when we do the Fourier transform, low-pass filter. But in fact, it's not going to be something we care much about for the applications where we use the Laplace transform. And let's just see how the Laplace transform is actually not very good for this signal. Why is that? Well, let's do it. What's the Laplace transform of this? Well, can anyone guess what the region of convergence is going to be? We can write out the Laplace transform. We always have this formula, right? It's what? It is. It is. All right, let me write out the integral here. Sinc of t e to the minus st dt. Now notice something here. Sinc behaves like a 1 over t in the positive t direction and like a 1 over negative t in the negative t direction. Okay, sinc tapers off. In both, it's symmetric, and it tapers off like 1 over t. So if the real part of s is strictly positive, okay, so if sigma is positive, we have a decaying exponential, okay, that should be fine in terms of convergence on the right side. But it's going to mess up convergence on the left side. Okay, so for positive sigma, this won't converge because the left side of sinc, I think you would see if you plotted like something like e to the sigma t sinc of t for any sigma that's not 0, sigma not equal to 0, you'd get something like this. You'd get your sinc. It would taper off real fast in one direction, and it would start growing in the other direction. Okay, and it would not converge. All right. So sinc, in some sense, just barely converges. And when you add any of these exponentials, it does not converge. So the important thing here is the ROC is values where the real part of s equals 0 and nothing else. Okay. We know what it is because we know the Fourier transform of it, so we know along this line it's rect. All right. So it's rect there. It doesn't exist anywhere else. If you tried to draw, often we'll try to draw these like pictures of the region of convergence, which aren't that interesting. They're just vertical strips. But in this case, it's just exactly that one line. That's all. So, question: if we use our stability criterion here, and I think this might be if and only if. I hesitate to put it because it's not in my notes, but that might be both necessary and sufficient. Okay. If we use this to say, is this system that has an impulse response sinc, is it stable? What would the answer be? It would be no, right? It would be no because it's not in the interior. All right. So that's just an example to show that edge case there. So sync is not actually something we'll be using with the Laplace transform. All right, let me try to get a couple more comments in here. So we have this. Now, the main things we will use the Laplace transform for are going to come in later lectures, next time and Friday. Okay? But we want to just understand these characteristics. Then we'll use them to analyze. Really, we want to use them to analyze systems and to design a system with a controller to be stable. That's what we would want. We'll barely get to that in this course. You'll hit it again in 301. You'll talk just about designing control systems. And hopefully the background you have here will make that very smooth. Okay, so often we characterize signals into these categories here. Very simple to understand. We say that a signal, and really these signals will actually be the impulse response of a system, and we'll care whether it's one of these things. Okay, so let's say right-sided. Right-sided signal, it's just what you imagine. I'll plot an example here. Here's T. And a right-sided signal just is something like this. Okay, it just means that there's some value of cap T for which it doesn't exist to the left of that point. Okay, so there exists a T such that x of T equals 0 for all T less than cap T. Now, this is the common way such a signal would be named. It would be called a right-sided signal. However, notice that the feature that makes it right-sided is actually that to the left it's 0. Okay, so the right-sided signal is defined by saying to the left of some point you're 0. You'll see because the naming, this conventional naming is sometimes going to be a little weird. So left-sided is exactly the opposite. That's easy. So it just means that there exists some T such that x of T is 0 for everything greater, for all T greater than that point. Now, two-sided means two-sided means an example of this would be like sync. Sync is one example. Of course, you can come up with tons of examples. And this means, what does it actually mean? It means that it's neither right-sided or left-sided. So this is where the naming is unfortunate, because mathematically, this is the precise way to say what it means, neither left or right-sided. But we call it two-sided, right? It's because, in fact, again, this is because right-sided is actually defined by what happens to the left, right? And left-sided is defined by what happens to the right. And we want it not to be cut off in either direction. So it's neither. Okay, so that's just some unfortunate naming there. And finally, for finite duration, and this means both left and right-sided. Although that's the mathematically correct way. All right, I'll say mathematically it means both the mathematical direction of left-sided and right-sided. Colloquially, of course, you don't really mean it to sound that way because finite duration means it stops both directions. And the reason the words right-sided is used, that's supposed to imply that it keeps going to the right. Okay, and left-sided is supposed to imply it keeps going to the left. Two-sided is supposed to imply keeps going in both directions, and finite duration means it doesn't go in either. But to be precise mathematically, you define it this way, and you find, oh my gosh, finite duration actually means it's both got the left-sided property and the right-sided property, right? And two-sided means it has neither of those properties. So there's sort of a difference between what you intend the words to mean and what the mathematics are. And so therefore, what we want to know is we can say certain things immediately about the region of convergence just based on if it, for example, is a right-sided signal. The region of convergence has no right boundary. Remember, the region of convergence is a strip, a vertical strip. It may or may not have a left or right boundary. And if it's a right-sided signal, it has no right boundary. And if it's left-sided, the opposite, right? The ROC has no left boundary. And then, of course, finite duration must mean the combination of these two things, because mathematically it means they're both true. So the ROC has no left or right boundary. Well, what's left? If it has no left or right boundary, it's the whole plane, or nothing. And like we said, it could be nothing, but it's usually going to be the whole complex plane. So then what do we say? So then what about two-sided? Well, two-sided just means we have nothing to say about the region of convergence. It could have boundaries, it could not. Okay? But it often will have both boundaries. But we can't say for sure, just because it's two-sided. So probably what I'm going to do is I'm going to go and add a little bit to this lecture, because there's one more thing I wanted to explain, and that is that we usually care about the Laplace transform for rational functions. I'll explain what a rational function is. And when we get to the applications, you'll see why we care about these rational functions. But we'll want to just understand how this region of convergence behaves for rational functions. And that's pretty much all of the tools we need for the Laplace transform to start going and using it. I guess we'll need some properties like the Fourier transform. That what does convolution do under the Laplace transform? But they're going to look very familiar. Okay, I'm recording a little bit extra on this lecture again. So let's go back and talk a little bit about why these properties hold. Notice that if your signal is right-sided, we're claiming that the region of convergence has no right boundary. What does it mean to go to the right in the S-plane? It means that sigma is getting larger. Remember that we're multiplying our signal by e to the negative sigma t. So what we're saying here is if it's right-sided, that means to the left it ends. Then increasing sigma just tapers off your signal even stronger. Okay? And by tapering it off even stronger, you can't make it diverge. If it's already converging for some value of sigma, then it's definitely going to converge for a larger value of sigma that just makes it decay faster. Okay? So that's why this exists. Same with left-sided, it's the exact opposite. If it converges for a particular value of sigma, it's going to converge also if you make sigma smaller, because remember it's e to the negative sigma t. So smaller sigma means exponentially growing faster. But since it's left-sided, the left side doesn't matter. It's just on the right side. And if it's growing, then it's shrinking to the left. Okay, so that's why that property holds. And there's no property for two-sided. And then for finite duration, of course, it can't, the only way it wouldn't converge is if it had a vertical asymptote. Otherwise, it's going to converge no matter what exponential you multiply with it. Okay, so it turns out what we really care about, first of all, let's mention causal. So what does it mean to be causal? Well, a causal signal, this is kind of funny because we talk about causal systems. What's a causal signal? Well, we're going to say a causal signal has x of t equals 0 for all negative t. Okay, why is that a causal signal? Well, really causal is just a system property. But remember, the impulse response of a causal system. So the impulse response of a causal system will always have the above property that we just mentioned. H of t equals 0 for all t less than 0. So really what we're just saying is we'll call it a signal causal with this definition. That way we can say an impulse response, we can say a system is causal if the impulse response is causal. Okay, just to give them the same definition. Okay, so great. So this implies right-sided. So causal system has a right-sided impulse response. Let me do that again here. Let me go back here. So let's talk about a system being causal. If a system is causal, we've already said that means that h of t
the impulse response equals 0 for all negative t. When we talked about causal LTI systems, we noticed that this is the requirement for a system to be causal, where that's the impulse response. So therefore, if that's true, then certainly the impulse response is right-sided. Okay, so a causal system has a right-sided impulse response. It's actually common to make a definition for a signal being causal. We would say that a signal is causal whenever this is true about it. So this is a causal signal. If the signal is 0 for negative values of t, then we say it's a causal signal. Now really that naming, causal is meaningless for signals. It's meaningful for systems. But you just name it this way so that you can, talk about the impulse response being causal. Now, causal is more than right-sided, right? Because right-sided, there just has to exist a value of t, such that for every t less than that, you have 0. Here, causal means that there's a specific value of cap t for which it has to hold. So a causal signal is a stricter statement than right-sided. But anyway, what's important is if your system's causal, the impulse response is right-sided. Therefore, if we're going to then look at the Laplace transform of an impulse response, we're going to see that for causal systems, it has no right boundary. Okay, so the last main thing we need to talk about here is a form of the Laplace transform that's going to be most relevant to us. Okay, so let's talk about what a rational function is. I'll say rational Laplace transform because really that's what we're going to care about. Okay, so what it means for a function to be rational is any rational function is a ratio of two polynomials. So we'll call it numerator divided by denominator. And these are functions, they're polynomials. Okay, so now we have that definition of a rational function. Therefore, now let's talk about what is special about rational functions. Really we'll see what's special about them in future lectures where we see that all the systems we care to analyze with the Laplace transform are going to be of this form. They'll be rational functions. The Laplace transform will be rational. But let's say, in general, this is just mathematics, doesn't have anything to do with the Laplace transform yet. Any rational function can be factored into a constant times the we can factor the polynomials. So let's say s minus sz1, s minus sz2, and so forth. A bunch of terms on top. And also you can factor the bottom. In this case, s is the variable of this function. And these sz1, sz2, sp1, sp2, these are just constants. So c is a constant. So those constants define the function. All right. And in fact, we would say that the number of terms is the order of the polynomial, of course. So you always get that many roots, the same as the order of the polynomial. But we actually call these roots of the numerator, so the roots of the numerator are szy, sz1, sc2, and so forth. These are the zeros of the rational function. And the denominator roots are the poles. Okay, now it's easy to see, of course, I've said that any rational function can be factored this way. The set of parameters here now is c is a parameter, and all of these SZs and the SPs are the parameters. They define your rational function. Okay, so really what that means is your poles, your set of zeros and your set of poles define everything important about the function except for this constant c, which often we won't care too much about. So let's look at the magnitude of a rational function. And that's just going to be, because these are products, the magnitude is going to be the magnitude of c times, of course, the magnitudes of all of these terms. And what's simple about this is you realize that, remember, this is a function of s, where s takes on values in the complex plane. And we realize that now the magnitude of this function, of this, if this is the Laplace transform, the magnitude of the Laplace transform is really just a product of, these are distances, right? This is the amplitude of a complex number. In other words, if we know where the poles and zeros are, let's draw an example here. So here's the, let's do this lower. Here's the real part of S. Here's the imaginary part of S. And now we're saying, gosh, if this complex valued function over S plane is actually a rational function, and if we factor it into poles and zeros, what we can do is, it's common to mark the poles and zeros using X's and O's. Okay, so let's say we have a pole there, some real valued S. Let's say we have a pole here and a pole here. And let's say we have a 0 here and a 0 here. Okay, and so this, by the way, this plot of where the poles and zeros are, assuming I did it precisely, and you could actually read out those positions, this plot actually specifies almost exactly the entire function, right? Because the entire function only depends on the locations of poles and zeros and on the on this constant factor c. So the only thing that's not in this plot is the value of c. Okay, so now if you want to know the value of this function at an arbitrary point, let's call that s, right? And we want to know how big, what is the value here? Well, it's got a magnitude and a phase. And we just derived that the magnitude is the magnitude of c, we'll ignore that for the moment, times the magnitude of these differences. So in other words, it's times the magnitude of the distance to the poles, to the zeros, distance to the zeros, and it's divided by the magnitude of the distance to the poles. So you take the length of each of these lines, and you multiply the ones for the zeros, you divide them for the poles, and that tells you the magnitude of the Laplace transform. So it's actually very intuitive, because now we see what's going to happen to the magnitude as you get close to a pole. As you get close to a pole, the magnitude's going to blow up. So you can think of these poles, and people think of them as tent poles poking upward. And you can think of the magnitude of S as some sheet or some elastic that is pulled down tightly over these tent poles, right? So the poles mark where the magnitude of S goes to infinity. And then you put stakes into your elastic sheet at the zeros, and that's where, because we know that the magnitude of this function has to be 0 at any of the zeros, right? Okay, so that gives you some sort of imagery of how to interpret the magnitude of a rational function given the placement of the poles and zeros. What about the phase? Well, the phase also is quite simple. Okay. So the phase is just going to be the phase of C plus, remember phases add, so the sum over all zeros of the phase of S minus SZI minus the sum of the poles of the phase of S minus SPI. So in other words, you just add all the phases for the numerator, subtract all the phases for the denominator. That's pretty simple, but how do we interpret that now on this plot of poles and zeros? Well, that means that each of these lines that I've already drawn, there's an associated angle right? That angle there is the phase of S minus SZ, whatever that 0 is. Let's say Z1. Okay, that's the phase. And we have another angle for the other 0. And we have an angle for each of the poles. And what we're saying is, you just take all of the angles for the zeros, and you add them, and you subtract the angles for the poles, and that's the phase. Okay, so we have like a geometric way of understanding both magnitude and phase just by looking at where the poles and zeros are. Of course, we know the entire function is defined by the placement of the poles and zeros. Now, let's now look at rational functions. Everything we talked about here was just general rational complex valued functions. Let's now look at this specifically related to the Laplace transform. So the Laplace transform, if it's rational, then it turns out that the regions of convergence are always defined by the placement of the poles. Okay, so rational Laplace transforms, we're going to find they're very easy. It's a good thing we're restricting to just rational Laplace transforms. First of all, they'll help us solve a lot of problems. And secondly, they're easy. It's an easy set of Laplace transforms to work with. So the boundaries of the region of convergence are always the poles. Okay. So, in other words, another example will help here. We have a real part of S here. We have the imaginary dimension here. Now, suppose that we have, I'll go placing some poles and zeros. So this is the rational function that is our Laplace transform. Okay, so you see we have 5 poles, 4 zeros. Okay, so aside from the value c, the constant c, this tells us exactly the function. Just the placement of the poles and zeros specifies the function. And it turns out that there are 4 different signals that could have this very same Laplace transform. Why is that? Because the regions of convergence are always bounded by the pole locations. And remember, they're always vertical strips. So in other words, there's this pole location. There's this pole location. Oops. Wow. There's this pole location. And there are 4 different regions of convergence associated with those boundaries. There's this one that just goes off to the left. It's not bounded to the left. There's this one. There's this one. And there's this one that's not bounded to the right. Okay, so 4 different signals can all have the same formula for the Laplace transform, but they would be different signals with different regions of convergence. So there we go. Just from the pole locations, notice the zeros didn't matter in defining the region of convergence. Only the poles did. And it makes intuitive sense that the poles are going to be at the boundaries of your region of convergence, because clearly the poles have infinite values there, which should ring out to you that that does not converge, right? So the poles are like points that do not converge. Turns out they define they're the only boundaries of the region of convergence. Okay, knowing everything we've learned, we can actually apply it and say that for example, we can quickly check whether a rational Laplace transform could correspond to a signal that is both, let's say, causal and stable. Okay, so let's do that example. So how do we check that? Well, we know that given the Laplace transform location of the poles, we know exactly which regions of convergence it could exist for that Laplace transform. And what that means is, now what do we know if the system is stable? Then we know That means its impulse response is right-sided. That means it cannot have a right boundary to its region of convergence. So the only causal signal of these 4 signals up here, the only one that is causal, or let's say could be causal, is yellow. The reason I say could be causal is because we know causal implies right-sided. Right-sided doesn't imply causal. Okay, the only one that could be causal is the yellow one here. All right. Now, okay. Now then we want to know, could it be causal and stable? Well, could this yellow one be stable? Well, what did it mean to be stable? It meant that the imaginary axis was in the interior of the region of convergence, but that's not true for the yellow one. So we know in this example up here, the signal could not be causal and stable. We know we have a right-sided signal, that's the yellow one, that's not stable. We know we have the purple signal would be stable, but it's not causal, it's two-sided. Okay, and we know that the green one would be both unstable and not causal. It's not right-sided or left-sided, so it's two-sided. And we know that the blue one would be a left-sided signal that's also unstable. Okay, so those are the possible signals we have. Now I said that causal, let me go back and modify one thing. It's true that the impulse response, okay, everything I said here is true. If it's causal, then it's right-sided. Turns out that if, additionally, the Laplace transform is rational, then the reverse is also true. If it's rational, then a right-sided impulse response will also be causal. Okay. Anyway, so what's the condition then, if we wanted to summarize, for a Laplace transform that could be both causal and stable? Could imply that the system is both causal and stable. The poles are in the left half plane. So if you forget everything else about Laplace transforms when you let's say after the final, when you finished this class and moved on in life, this is probably the most important thing that you can retain for future applications, is that the Laplace transform of a system, meaning the Laplace transform of the impulse response of a system, can be causal and stable if and only if all poles are in the left half plane. That means all poles are to the left of the imaginary axis. That is what people remember about designing, control and designing stable systems. They just remember that one rule: poles in the left half plane for the Laplace transform.